Today we're going to be covering CSPs, but possibly just as importantly, you're all halfway through the quarter, so congratulations. I think 6 more weeks to go, so keep it up. Also, happy Halloween. Hope you all have fun. But today we're going to be talking about CSPs. So this is continuing these topics that we've been covering since Monday, which is about this kind of setting, right? So you have variables. In this case, we have 3, x1, x2, and x3. And each variable represents some kind of discrete object that can take on one of several values. And so the set of values that a single variable can take on is called its domain. And just to continue reviewing, these variables have factors, which are functions that take as arguments one or more variable. And the factors basically say, OK, how much do I like this assignment of my variables? So for example, factor 2 looks at x1 and x2, and it says, OK, x1 has been assigned some value. x2 has been assigned some value. How much do I like that assignment? Do I really like it? If so, you give it a high value. Do I not like it? If so, you zero it out. And so importantly, we call the arguments, so all the variables that we give to a factor, that's the scope of that factor. So we had this example that we talked about on Monday, and I'm just going to revisit it. So in this case, we have variables correspond to people, and there's 3 people. And we know that, first of all, the first 2 people, person 1 and person 2, they have to agree to each other. And then person 2 and person 3, they sometimes agree with each other, but not all the time. And so first what we say is with our first factor, we say that person 1 is definitely blue. So we say this here by saying these are the values that the variable can take on, red or blue. And this is how much we like that value. And what this first factor is saying is that it doesn't like red at all, it's a 0, and it likes blue, it's a 1. And then we have the second factor. This encodes the fact that they must agree. And what that's saying is that every time both the first variable, which is x1, and the second variable, which is x2, every time they agree, they're either both red or both blue, we give it a 1. Otherwise, we give it a 0. And then we have this factor, which says that they tend to agree. And we're encoding that by saying, well, if both of its arguments are the same, if they're both red or they're both blue, then we give it a slightly higher number than if they differ. But we're not going to zero it out. And then last, we say, OK, well, the last person kind of prefers to go red, but it's not a hard constraint, nothing like that. And so then, again, so like we talked about last time, assignments, which is like if you have all your variables and you have all the values that you've assigned to them, they have what's called a weight. And a weight is basically just plugging in all the values for your variables into your factors and then multiplying them all up to get that product. And that's the weight. And our goal across all of these problems in this whole unit is to find assignments for all of our variables that'll give us the maximum weight when we multiply up all of our factors. Yeah?
Is there any particular reason the weight is defined as a product as opposed to a sum?
Yeah, so the question was, why is the weight a product and not a sum? And the answer for that is because, remember, these are constraint satisfaction problems. And so if you look back at this example, we wanted to encode the constraint that they must agree. And we did that by putting in a 0. And since we're multiplying it up, if you have a single factor that gives a 0, it's like a veto. And so that veto power is actually really critical. And we leveraged it on Monday, which I'll talk about soon. So on Monday, we talked about one algorithm for solving these kinds of problems. We called it backtracking search. And it's a kind of an exhaustive, you could think of it as like a depth-first search of all the possibilities. So we have this example from last week where we were coloring provinces in Australia, right? So we have, I actually don't know the provinces of Australia, but we have WA, and we have V, and we have T. I think T is Tanzania, Tasmania. I'll work on my geography. But we color them all red, right? And so what we decided to do was we decided to, hey, we'll color Q red, let's do it. And then we say, hey, if we color Q red, let's go with green here for NT. And then we pick blue for SA, and then green for NSW, and we've completed that tree. We've gone as far as we can. We've found a coloring that works. We say, oh, wait, what if we backtrack up to this point and try to sub in blue in for NT instead of green, which is what we had before? And then we can do the same thing. We go down that branch of the tree. Or we could try different colors for Q. So for example, what if we try Q over here? We take that tree down. Oh, but that gives us something that is not satisfiable. So for example, here in SA, no matter what color we give it, according to our factors, which say like you can't have two neighboring colors, it would be not allowed. And you fill out the tree this way. And so this is the algorithm we covered. And it works because it always gives you a good version, but it's not working because it's super slow. It's exponential time. So there's n nodes, and each node has a domain. And so it's like for each value of, here, I can draw it out. So like, for example, if we had two variables, x1 and x2, and they both took on 3 values, so these are our variables, and these are the values they can take on, and these are how much our factors like them. Then you would have to say for each value in x1, for each value in x2. So it's this exponential blow-up, which is just very slow. And so we learned some kind of like heuristic ways to speed things up and prune off that tree. So we did forward checking, which is where like once you decide my value for one variable, I'm going to go ahead and propagate that decision as far as I can. That shrunk it a little bit. We looked at dynamic ordering, which is like, OK, which variable am I going to choose to work next? And then once I've chosen that variable, I'm going to choose my value a little more intelligently. I'm going to pick the thing that has the least wiggle room, because maybe that'll help us. 1 second. And that helped us a little bit. But at the end of the day, these constraints, they helped us prune the tree, but they can only work for constraints. Only if a factor gives us a value of 0 does it work, because that's when it has veto power. And we use the vetoes to say this branch of the tree will never be useful, so we can never go down it. So if we have factors that are going to be non-zero, we can't use any of these things. Yeah?
More on the example of how you got the numbers. So like for one variable, there's only one, and then I guess it's 2 to the n minus 1.
Yeah, so for this, I guess this example, what it would look like as a graph, I guess it wasn't the best example, but, and actually later in lecture today, we're going to talk about exactly how you could go about this more smartly. But let's say you just had 2 variables. They each had unary factors. If we were running binary, like backtracking search, we would still say, we would try all different combinations of both variables, which is a very dumb thing to do. Yes, so that's backtracking search.
Interesting.
Yeah, so we'll discover smarter ways to get around that. Yeah, so that's backtracking. Slow, but it gives you the optimal solution every time. So maybe a mixed bag. OK, so I'm going to lead into, this is a running example that we're going to be talking about the whole lecture, object tracking. So with object tracking, you have sensors that are telling you like, oh, my object is here. No, it's down here. Oh, wait, it's over here. And what you want to do is you want to take that noisy observation and run it through your CSP to infer a more realistic estimate for where the object actually is. So I will also draw this on the board. So what this looks like is if we have, this is time, so we'll call it t for time, and this is position, so we'll call it p for position. And what this is going to say is we have sensors that are giving us estimates, like noisy estimates for where this thing is at every point in time. So for example, maybe at time step 1, we get an observation down here. At time step 2, it's up here. And at time step 3, it's up here. But in reality, like we want maybe something more like that. And so that's going to be our goal with this running example. So this is how we code it into a factor graph. In this case, we have variables where the variable is our guess for the real location for that object. We have two kinds of factors. We have unary observation factors that say how close is our guess to the observation, to what our sensor said. And then we have transition factors, which basically tell us you can't change your guess by too much from time step to time step. So on this graph, what it would look like is if these are our observations, so this is like O1, O2, and O3, then maybe our first guess would be here. So we have x1 down here, we have x2 down here, and then maybe like x3 up here. And so our observation factors is going to look at this distance. And that what this is going to say is, OK, how far is our estimate from the observation? And they want that to be close. And then our transition factors are going to look at this distance between one guess and the next guess and say, well, our guesses shouldn't be moving too much. Yeah?
What's the difference between the observation and estimate?
So the observation is what the sensor gives us, and the estimate is us saying thank you thank you, sensor. Now I think the person is actually right here, because the sensor is noisy. We can't trust it. Yeah. OK, so that's how we're going to set up this problem. And I think so. There's this really cool kind of like Java applet that you can all play around with on your own time. And I will briefly walk you through it. So what's going on here is basically, so there's a lot of documentation that you can read. But basically what's happening here is we're just creating these variables. We have 3 variables, and we're allowing them to go in 3 positions. So in position 0, 1, or 2. And then this is a little function that's basically encoding the fact that if things are nearby, then we like that. So we have 2 variables, a and b. And if they're in the same position, then we return 2. We really like that. If they're only 1 away from each other, we return 1. So it's OK, we'll take it. And if they're farther away than 1 from each other, then we zero it out. That's a hard constraint. We don't like that. And then we have this observe function, which is kind of a higher level thing. And it kind of, I guess you could say it kind of like preloads our nearby function with a variable. And we're going to create our factors. And then this is what it looks like. So we have 3 variables. We have x1, x2, and x3. And then we have our observation factors are unary. Remember that say, OK, you have to be close to the sensor. And then our transition factors are binary. And that says you can't move too much between time steps. And you can run it. And there's actually a lot of output here. And I'm going to ignore most of this for now. I think the thing that is important here is that we ran backtracking search, and we found the optimal assignment. So in this case, it's 1 for x1, 2 for x2, and 3 for x3, which gives us a final weight of 8. So on our little drawing, basically what that's saying is it's saying something like this is optimal, where we say, thank you, sensor, for these estimates, but we think the person is actually here at time step 1, here at 2, and here at 3. That's the solution that backtracking gave us. Yeah.
What do you mean by the here at 3? Because it was 2 and 2. So either those are the weights or the time steps, because you were saying it's like 1, then 2. So x1, 1 is a time step 1, and then x2 is time step 2, but x3 is also time step 2.
Yeah, so the question was, what do you mean by here at 3? And what I mean is basically, so xi is our estimate for the position of this object. And so at time step 3, our estimate for the position is at position 2. And
Same as here for x2.
Yep, so x2 and x3. So that's why there's x's at 2 for both time. These is like time step 1, 2, and 3. Yeah. Yeah?
So I understand like what you're talking about with the scope of the factors, but how exactly is there a constraint being imposed by the problem?
Yeah, so the constraint here is, so the fact that if we look at our nearby function, and if a and b are farther than 1 away from each other, then it returns 0. And that's a constraint, because when we're calculating the weight of a factor graph, we multiply together all the factors. And so if there's a 0 in there, then the whole weight goes to 0.
Constraint only for the transition factors, but not the observation factors.
Yeah, yeah, you could say that. Yeah. Great. OK, so that's our setup. And we're going to be returning to that a few times. Awesome. OK, so moving on. Backtracking search, very slow. Let's try to speed it up. Beam search, faster. Yay. Beam search, so backtracking search, we have that tree analogy, right? And backtracking search exhaustively searches the entire tree. Gets us the best solution, but it's very slow. And so one way to avoid this kind of like exhaustive search is greedy search, which is where you greedily, it's like, for each variable, you greedily select the value that gives it the highest weight. So it's right here. You look at the values it can take on, and you just choose whatever value is best. And you never look back. You just keep on running through it. And you go through the whole tree this way until you end up at a complete solution. So the benefits is it's very fast, right? It's linear. But the con is that it's a very narrow window. Like you don't see a lot of the state space. You don't explore a lot. And so you can often miss the global max. So for people who prefer this kind of notation, what we're doing is we basically say we loop through all the variables, and we try out every value, and we just take whatever value has the highest weight. Yeah. So beam search is kind of like an in-between backtracking and greedy. Beam search is very cool. So one way to think, yeah.
Again, how we are doing that?
Yeah, so the question was explain greedy again. And so with greedy, what we're doing is we say, so we have a partial assignment, right? And we want to extend our partial assignment. So we pick a new variable, and we try out every single value that variable can take on, and then we take the value that gives it the highest weight. So all the factors touching that variable are the most happy with that value. And we pick that, and then we never look back. And then we pick a new variable.
Like inconsistent solution. We can end up at an inconsistent solution where I cannot choose any value.
Yeah, so that's a good observation. We can end up at inconsistent solutions, and that's totally true. So you can during a greedy search, you can actually kind of like find your way in kind of a hole where it's like, oh damn, I can't go any further, and it's a big problem with greedy search. Yeah. So with backtracking, beam search is kind of like a heuristic way to maybe get around that. So with beam search, so remember again so for greedy search, we had one partial assignment, right? And we were choosing one variable and choosing an extension of that one variable. With beam search, what you do is instead of one partial assignment, you maintain a list of k partial assignments. In this case, k is 4. And then what you do is on every step is for each of your partial assignments, you pick a new variable, you try out all the ones, and then what you do is you have your k partial assignments, and you try to extend every partial assignment. You test out all the values for every partial assignment, and then you sort those partial assignments based on their weight, and then you just take the top k. So it's like you have your partial assignments, you extend them into all the possible successors, you sort them based on weight, and then you take the top k. So in this case, if we have 4 partial assignments, then we try extending them all in the 2 directions they can go. And then we sorted them, and then we took the 4, you can see there's 4 things that are filled in that have the highest weight. And we continue this procedure. So we say, so what we would do in this case is we would say, okay, for each of these 4 solid things, we're going to extending each of those partial assignments, and then we sort all the extensions and select the top k. So, yeah.
So like after the top k, because when you start, if there's not k partial assignments yet, you just select all of them.
Yeah, exactly. So the question was up to the part k, right? And the answer is yes. Yeah. So for example, here, 1 is less than k, so we extend to 2. 2 is still less than k, so we can extend completely. So in notation, so we say for each variable, we try to extend each of our partial assignments, and then we prune out everything but the k largest, the best k weights. So beam search is also not guaranteed to find the best weight. But what's cool about it is that it gives you kind of like a knob that you can control between being greedy and exploring a lot. So if k is very wide, then you explore more and more of the tree. And if k is actually infinity, I think this is on a slide soon. So if k is infinity, then that's actually like akin to a breadth first search of the entire tree. Yeah.
So on that graph, or on that picture where you had like the solid and the shaded out ones,
Yeah.
for the shaded out gray ones, we would actually never explore those.
Yeah, so this picture, I don't think it's the best picture because, so for example, okay, so I'm looking right here, and in reality, you would never extend this because it was never selected.
But you still initially explore it and then find that it's not.
Yeah, so up here, so at this point, we do consider it because we extend down, but then we decided not to select it. Yeah. Awesome. Runtime. So for beam search, you're selecting a single node, and then for each partial assignment, you're trying out every value in the domain. So if b is the size of your domains, then you're trying out b things for every partial assignment, and you have k partial assignments, right? So those are the number of extensions you have is kb. And then you sort them, and to sort, if you have a list of length n, sorting it is n log n. And so you sort your list of kb, so that becomes kb log kb, and then there's n nodes that you need the height of this tree is n. So you do this n times. So like I said, beam search, the k gives you this really cool knob between do you want to explore everything or do you want to focus in on being fast and greedy. Okay, so everything until now, what we've covered is extending partial assignments. So we're giving like a blank slate, picture of Australia with no colors, and we say, color me Australia. Like build up this house from the foundations. And now what we're going to talk about is, okay, given like a map of Australia that's already filled with colors, how do we make changes to it in order to improve it? And that's local search. So the first algorithm is called iterated conditional modes, ICM. And what ICM is doing is it says, okay, we pick one variable, and then we ask, what is a new setting that we could choose for this variable that would improve the overall weight? So in this case, we have one variable, it's x2, and we try out all the different values it can take on, which is 0, 1, or 2. And then for each of those values, we go through and recompute the weight, and then we pick whatever value is best. So we started with 0, 0, 1, and here it looks like 1 is a better choice, so we go with it. And from now on, we would say x2 is equal to 1. So something cool about ICM is that when you're evaluating a new value for a variable, you only need to consider factors that touch that variable. That's all you really need to recompute, because everything else is constant with respect to it. And so that gives you big, big, big time savings in practice. One last thing is, so the name iterated conditional mode. So iterated comes to the fact that you could solve the whole CSP this way. If you just iterate over which variable you're selecting. Conditional means that once you select a variable, you're clamping down the values of everything else. And then modes is saying once you've selected your variable, you try out every single value for that variable. Yeah?
You just like kept doing this with every variable, would you eventually like arrive at the optimal solution, or could you like kind of like end up in like a cycle?
Yeah, so the question is, if you have your 3 variables and you keep on going through them and choosing one, clamping the others, and then choosing the best value for it, would you arrive at an optimal solution? And the answer is no. And we'll see that in practice, yeah. Yeah, so again, this is just to give you the notion that we iterate through these variables, and for each variable, we pick a weight that improves it. So we have this in the demo. So in this case, what's going on here is we're saying, OK, right now we've selected, we're looking at x1. We start with a random initialization. We're looking at x1, and these are the different values that x1 could take on. And then we go through and calculate the weight. And we say, OK, 1 is the best weight for x1 right here. So we choose 1 to be x1. And we step again. We're looking at x2 now. And oh, it looks like actually a value of 1 is better for x2. And so from now on, we choose the value of 1 for x2. And we iterate again. Now we're looking at x3. And it looks like we choose the value of 1. And you just keep on iterating for this until you hit some kind of local optimum. And what I'm saying, this is important that it's a local optimum, because right now it's converged. So I can keep on pressing step, and it's not going to change. But the weight is 4. And if you remember, during the other thing when we ran backtracking, we actually found an assignment with a weight of 8. So it can fall into these local optimum. One way around this is a second algorithm called Gibbs sampling. With Gibbs sampling, what we do is we inject some randomness into the process to try to like bump us out of those local optimum into something that can maybe get us into a better area. So basically, Gibbs sampling is super similar to ICM. The only difference is that so you try out all the values, and instead of selecting the value that gives you the biggest weight, you sample the value with probability that's proportional to its weight. So for this example, we say a setting of 0 would give us 1, value of 1 would give us weight of 2, value of 2 would give us a weight of 2. And then to get the probabilities, we take the weight and we divide by the total, which would in this case would be 5. We sum them all up and divide by that. That gives us a probability 0.2. So here we say it's 2 divided by 5, which is 1 plus 2 plus 2. And then we use that probability distribution to sample a new value for x2 instead of just choosing and saying, oh, you're the best. So this is the demo. So in this case, we're looking at x1, and we're trying out different probabilities for it. And we have weights, and then that gives us a probability distribution. And we sample from this probability distribution. So in this case, it looks like we sampled, and we chose 0 for x1. And then we keep a record of how many times we've ended up with a certain assignment. So if we step again, now we're looking at x2. It looks like x1, a value of 1 is the only thing that works. So we choose that value, and we add it to the counts. And you can just keep on running this process. And over time, you build up this kind of like probability distribution. So this is actually an unlikely sample. So it had 20% chance of choosing 1 and 80% chance of choosing 2, but it still chose 1. And that's a way that it can kind of like break out of these local optimums. But in any case, if you look at this table, then what you find is that over time, if you run this thousands, millions of times, then in practice, settings with very high weights will occur very often. And actually, when we get into probabilistic graphical models, which Percy will talk about soon, you could actually say that the global optimum will be the most frequent in Gibbs sampling in the limit, which is, I think, pretty cool. Yeah. OK, so just to show an example of what can go wrong with this algorithm, it's still flawed. So if we have x1 and we have x2, and let's say it's two people and they're trying to decide where to go to dinner. So we could have, let's say they're deciding between vegetarian and going to a steakhouse. So we have V for vegetarian and S for steakhouse. And they really both want to go to vegetarian, and they want to eat together. And they'll eat steak, but they're not super crazy about it. So if you're in this state, then even if you're doing Gibbs sampling, it's really hard to bounce over here because you have these two kind of like transitionary settings in between. And in order to make it to both vegetarian, one is going to have to make the decision to go to a different restaurant. And so since this is so low priority, it's going to be very difficult for these two people to go over to vegetarian. They're both kind of like, oh, I want to do what you want to do. You want to do steakhouse, right? I want to eat together. You want to eat together. Let's do steakhouse then. And they both don't really know that they would be much happier overall if they both ate vegetarian. And then this would really be even worse if you had, so for example, if you had like zeros here, then there's actually no way for them to get there because there's no probability there. Yeah.
So this is saying it's basically very initialization like centric. Like whatever you pick as your initialization is going to be very important because if you initialize to the state where they're both vegetarian, then you'd never want to leave and you'd be happy never leaving. But if you initialize to both steak, then you're in trouble.
Yes. So in general, in optimization, in any kind of optimization area where you can have this problem of falling into some kind of local optimum that's worse than the global optimum, it's very dependent on your initialization. Yeah, because if you initialize over here, then you would fall somewhere lower, just by chance, yeah.
What would it be like if you initialized at like SV or VS, where you initialized to a state where it was 0? Would you have an equal chance of going either one?
So the question was, what if you initialized into a state that had 0 probability? So what you would do is you would select a variable. You would select S1, and then you would try out different values for this. You would say, OK, I'm going to either choose S or V, holding x2 constant. And in that case, transitioning to V would have a probability of 1. So you would do that almost deterministically.
And should we be thinking of those numbers as probabilities or rewards?
So for Gibbs sampling, these are probabilities. You turn them into probabilities. Yeah. Yeah.
So just to clarify, Gibbs sampling is not guaranteed to find the best assignment, right?
It is not guaranteed, yeah.
But you mentioned something like in the limit it is.
Yes, but that's not like that's kind of a theoretical point. It's not really practical. Yeah. So in the limit doesn't mean like a guarantee, I guess. Yeah, I guess you could interpret it that way. Yeah, so I guess this is directly about your question. So if you were to compare these questions, which ones are guaranteed to give you the maximum weight assignment? And the only one is backtracking search. Because greedy is too narrow, beam search is maybe too narrow, ICM is too myopic, and Gibbs sampling is, it's not a guarantee. It's likely, but it's not guaranteed. Yeah. Sorry, can you say it again?
For this example, even in the limit, it won't converge to the optimum.
Yeah, so the question was, in this example, even in the limit, you wouldn't converge. And that's true. So if you initialized right here, there's no way for you to get over there. Yeah. So yeah. I think it's just in certain conditions. Yeah. So that my intent wasn't to confuse you guys. So it was a theoretical point for like some subsets, some CSPs. Yeah. Yeah.
Like you said, if we suppose initialized at steak, there's no point that we can go to like vegetarian, right? Because in the middle transition probabilities are 0. So is it like safe to say that when you are modeling a problem with Gibbs sampling, you should never, like, even if you encounter probability 0, just give them some epsilon probability so that there might exist some chance to go to the optimum?
Yeah, so the question was, is it worthwhile to add some like plus 0.0001 to these just to give it some probability? And my intuition says sounds like a pretty good idea. It sounds kind of like adding tiny little epsilons to avoid division by 0, but I think it would depend on the problem that you're solving. Well, you could imagine some cases where you would really want those zeros. OK. So just to summarize so far, we've learned 2 ways of extending partial assignments in these graphs. So one is backtracking search, which we learned last time, which is like a full search of that tree. Gives you the exact solution every time, super slow. Beam search is approximate, and it gives you this cool little knob to trade off speed and, I guess you could say, like success or exactness. And then second, we learned ways to give in an assignment to improve it, to modify it. One was ICM, which was approximate. And then the other is Gibbs sampling, which is also approximate, but it uses some probability, some randomization. And now what we're going to look at is we're going to look at 2 ways to solve these kinds of problems by actually changing the structure of the graph itself. So our motivation comes from Australia. Tasmania. That is the motivation. So Tasmania, if you remember, was completely disconnected, right? So I think we colored it red in the previous example, but it doesn't really matter what color we gave to it, right? We give it anything we wanted. And so what we want is we want to kind of leverage this property, and more than leverage it, we want to kind of like inject this property into graphs that don't exhibit it. We want to like build this probability and this property out of graphs. So first we want, like, what is this? It's called independence, and it can speed things up. So just like I said before, so is it still there, my old? Oh, it's partially erased. So if we write this down again, so this is the same example as before. We have 2 variables, each with a unary factor on it. With backtracking search, I told you what would happen, right? You do something really dumb, which is it's like 2 for loops, right? You try out every combination of them, which is exponential. Whereas what you could really do is just say, OK, for each thing, I'm going to choose the value that maximizes, that makes my factor most happy. And that's linear time. And so that would give us a more efficient algorithm. Oh, no. OK. And we call that property independence. So so in this case, x1 and x2 are independent. And the reason that they're independent is that there's no factor connecting them. There's no paths between them. And there's no edges between them. And so we call that independence. And that's the same thing with Tasmania and the rest of Australia. So I don't know how independent it is, like culturally or politically, but it certainly is in terms of like map coloring, graph theory-ness. And in symbols, so we use this kind of cool-looking pipe thing, and that denotes independence. So yeah, so like we said, Tasmania is independent. What about cases like this? So it's not quite independent, but it's almost independent. You know, only if x1 didn't exist, then the rest of them would be independent. And so this is where we introduce this idea of conditioning. And conditioning is a way to rip nodes out of a graph. So, and we do that by saying, OK, in this example, let me draw it up. So there's x1 and x2, and then it's 1732. 1732 and red. Oop. So 1732, red, 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 blue, blue, red, blue, blue. 2, 3, 7, 1. OK, so we're saying x1 and x2 are connected to each other with a factor, right? But what if I say x2 is definitely blue? Yeah.
Constraint satisfaction problems, but also like graph problems as well. Like, are all constraint satisfaction problems, can they all be written as like graph problems?
Yeah, so the question was, can constraint satisfaction problems be written as graphs? And as all of them. Yes, yeah, because variables are nodes and factors are edges. Yeah. So it's actually a really elegant way to think about it, because then you can bring in all this graph theory stuff. Can you also see the board? OK. I'll try to write big. OK, so if I say x2 is definitely blue, like trust me it's blue, then what does that let me do? It lets me cross out all the rows where x2 is not blue. So here, x2 is red. So I can be like, you are never going to happen. I know you are not the case. You are not true. And for you, same thing. You are not happen. And now once I've fixed x2, all of x2's values are the same. So this doesn't really add information to this table. And I can just drop that data from the table. And what that gives me is it gives me a reduced table, which is just a unary factor of x1. And it can take on red or blue. And then I have a value of 7 if I choose red, and 2 if I choose blue. And graphically what that looks like is I'm deleting x2, and I just have one factor now, x1, and it has a unary factor. Now, the price to pay for that was I had to assume that x2 was blue. I had to condition on x2 being blue. So notationally, or maybe like programmatically, I think a good way to think about it is it's kind of like you're taking the factor that touches x2, and you're kind of like preloading it with a value for one of the arguments. And then the rest of it is untouched. So you choose a value for a variable. You remove the value, the variable from the graph, and then you stick in that value. You preload the associated factors with that value. So for example, if we were to condition on these, then I'm saying SA is green and Q is red, trust me. And then what that does is it rips those out of the graph, and everything touching those conditioned variables turns into some kind of a stump, and you preload the value for those variables in. The only edge that gets removed here is the one that connects SA and Q. And that's because you have a function that takes 2 arguments, but you've preloaded both of those arguments already, so it's done. There's nothing to do there. Might as well not exist. Just an example of the new factors that go in. So NT, for example, this factor, which used to say NT and Q can't have the same color, it turns into this little thing, which just says NT can't be red. And you know that because you're assuming that you're conditioning on the fact that Q is red. Yeah?
Independence, is it like 2 variables have no edge between them or no path that can connect them in the graph?
Yeah, so the question was, is independence no edge? Is independence mean, is there no edge between them, or is there no path between them? And we will talk about that. So for independence, you would need both true. But then we're going to cover another form of independence called conditional independence, which is just the latter. Yeah?
Wait, how is this different from the idea of extending partial assignments? Because aren't you like starting with partial assignment on the graph and then kind of exploring or optimizing the rest of the nodes based on that partial assignment?
Yeah, so the question was, how is this different from extending partial assignments? And it's not. So that's actually a good point. I think, so conditioning might actually be a case of building up partial assignments. I think the main thing to think about is now we've kind of like moved on. So extending partial assignments and modifying existing partial assignments, that was kind of like our old world, which is where like this graph structure is very perfect and we can't touch it or change it. Now we're in a new world where we're allowed to change the structure of the graph. And so we've kind of like left that way of thinking. Yeah. Yeah.
What drives the decision-making process of like setting it to green or setting it to red?
what drives the decision process of choosing these values. We will get into that. Yeah. Yeah.
And how did you know exactly to condition those two, and that you'll end up in a independent result afterwards?
Yeah, so the question was, why do we choose to condition these? So in this example, it's arbitrary, but soon we're going to cover ways of choosing them. Yeah.
How is it different from forward checking?
What?
How is it different from forward checking?
How is this different from forward checking? So in forward checking, what we were doing is we were propagating the decision forward to reduce the domain of existing factors. Whereas in this one, we're changing the structure of the graph itself, and we're literally removing variables and inserting new factors. Okay, so to move on, graphically, in general, what this looks like is if you have a variable that you want to condition, you rip it out of the graph, and then everything that touches it turns into some kind of a stub with the value preloaded in there. This is just a picture of the same idea. Yeah, so I guess you could say this is the big difference, is that whereas in forward propagation, we were keeping the existing graph and we're just propagating our decisions to reduce domains, whereas now we're literally removing this variable and the factors with it, and then we're adding new factors that are preloaded. Okay, so we are going to now go to what you were asking about, which is conditional independence. So if you have three variables, A, B, and C, so let's say we have A, C, and B, then you would say that A and B are conditionally independent. Because once you condition on C, once you pick a value for C, remember, these turn into stubs, or stumps, or whatever you want to call them, G's. And so these are now independent. They used to not be independent because they could access each other through C. But now they're independent. There's no edge connecting them, and there's no way to reach each other. And so this is just a way of formalizing that. This is how we write it. So we condition on C, and then A and B become independent. Yeah, so equivalently, you say every path from A to B goes through C. And then that means if you remove C, then there's no path connecting them. So in this example, you have SA and Q. If you condition on them, then you rip them out of the graph, and then it looks like Western and Eastern Australia are now independent of each other because they've turned into islands. And that's writing it mathematically. So there's another notion of a Markov blanket, which is basically saying, okay, I've chosen some subset of the graph, in this case it's V, and I want to make it independent. What are the variables I have to destroy in order to make my variable an island? So in this case, it would be SA and NSW. If you condition on these, then V becomes an island and it's independent. If you wanted to make this subset independent, then you would condition on Q and SA. And the set of nodes that you have to condition on is called the Markov blanket of the set of nodes that you want to be independent. So it's like if you have some part of the graph A and you want to make it independent of a part B, then C is kind of like the Markov blanket of A if when you delete it, A becomes independent of C. This is kind of like a set notation thing. It's a set difference. And this is just a way of writing it more mathematically. So we can use these ideas to like create independent structures now of our data. So we had this example before where it was almost independent, but not quite. Now what we can do is we can condition on it, So we condition this to be red, and then we can find the maximum weight assignment of the rest of it, which we showed was easy before, right? With this example, it's just linear, like what's the best for you, what's the best for you. So once we condition on this thing that's making it non-independent, then the problem becomes very easy. So what we do to solve this is we just condition repeatedly. We say, OK, I have picked my node. Now for red, green, and blue, solve it. Condition and solve, condition and solve, condition and solve. And this becomes very quick. And then you can read off the maximum weight very easy. You just say, oh, it's green, because that was the maximum weight I found once after conditioning. Yeah?
The weight there to the weight, the sum of the weights for all of the variables, just for one.
So the product of the weight. So the question was, when I talk about weights, what does that mean? And it's kind of loosey-goosey. It's not very formally defined. But in this example, I would say it's the weight of the whole graph. So you condition on this, and then you find the best values for all of these variables, and then you take the products of all of those unary factors, and that gives you the weight.
Is this just an example, or is this actually what the numbers would be? Like what was
This is just an example.
Okay.
Yeah, the numbers are arbitrary.
Okay.
Yeah, yeah.
So if you are going through R, G, and D, isn't that the same as doing like all the possible combinations anyways, like computationally?
Yep, it is. So it is. So you cover every solution that backtracking would give you. This would give you too. This is much faster, because what you're doing is you're taking a very complicated problem and you're breaking it into easily solvable pieces. You're taking an exponential problem and you're breaking it into a linear number of linearly solvable pieces. And in practice, it's much faster.
It's more just like an implementational distinction rather than a like space search distinction.
Yes. Yeah, you can say that. Yeah. Yeah.
So adding on to that, it's essentially that instead of doing all possible assignments for all of the variables, you're just choosing a subset of them to like exhaustively search.
So the question was, instead of exhaustively searching all variables, you're exhaustively searching just a couple variables. And yeah, that's an interesting way of thinking about it. I think in both ways, if you think about it, it's like, even if you're conditioning, for every single variable, you're eventually going to consider all of the values it can take on, but you're reordering things in a way that's much smarter, and that lets you take advantage of this independent structure in order to do it better. Yeah. Any more questions on this? Yeah, so it is faster than backtracking. And you could see it here. So for example, if we did backtracking here, it would be, there's 3 colors and there's 7 nodes, so it would be this huge exponential blowup. Whereas if we condition here, then it becomes much smaller. OK, so just to summarize, independence is when we have A and B, and there's no way to get from A to B. Conditioning is when we take a variable, plug in its value, rip it out of the graph, and then preload all the factors that touched it. Yeah.
I just have a question on the last slide.
OK, I'll finish this first. Conditional dependence is when you have 2 blocks in your graph, and if you condition on one part of your graph, then if you rip that out, then these 2 become separated. And then a Markov blanket is saying, OK, I want to make my variable an island. What nodes do I have to destroy to make it an island? Yeah. What was your question?
I guess I'm unsure why it's computationally cheaper, because if you condition on x1 for each of the colors, you still have to you still have to come up with 3 sets of unary factors for each of the below variables and iterate over each of their domains. So it also seems exponential.
So in this case, doing backtracking, so if we did backtracking, that would be what, 7 to the 3rd, right? Is that true? 3 to 7? Yeah. And then if we did conditioning, so that'd be 3 for the first condition, right? And then every time we condition, we do 7 times 3, right?
6 times 3.
6 times 3, yeah, you're right. 6 times 3. So this is 6 squared. Right? What?
Is it still 6 times 3 or times 2?
6 times. It depends. I don't know exactly what these factors are saying. This it's kind of an arbitrary example, but I think the point here is that this is smaller, right? So this is 3 to the 4th or whatever. So it's faster. Yeah. Yeah.
Can you explain how you're getting that value or that computation? Like for the condition.
Down here?
Yeah.
Yeah. So this is saying that there's 3 colors for x1, and then every time I choose a color for x1, I'm saying that there's 3 options for each of the 6 other things. So once I've set x1, it turns into this situation, where now I'm saying, what's the best value for x1? Okay, so I look at 3 things and choose the best. Now, what's the best value for x2? And I look at 3 things and choose the best. And so there's 6 of these, and for each item, I have to consider 3 different possibilities. Yeah. It would probably be different depending on what the actual factors are and what they're calculating, but it's just an arbitrary example. Okay, so now we're going to do elimination. Elimination is very cool, I think. So conditioning is saying I'm going to rip my variable out of the graph, and then I'm going to plug in whatever value I conditioned on into all the neighboring factors. What elimination says is okay, I'm going to rip my variable out of the graph, but instead of plugging in a single value across every single factor, I'm going to plug in a different value per factor in order to individually optimize each decision. So I think it's best shown through example. So again, this is the thing. We have 2 variables, and they're connected by a factor, and they have these weights. If we condition, then I think this is this example, right? So if we condition, we get what we got before. And then if we eliminate, here, I'll do the elimination now. So I'm going to redraw this table. So we have x1 and x2. We have red, 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 blue, blue, red, and blue, blue. They have weights of 1, 7, 3, and 2. Okay, so what elimination is going to do is we condition, it like internally optimizes the value that we want to condition on based on the other arguments in that factor. So we would say, okay, we're trying to eliminate x2 right now. And we do that by looking at each value x1 could take on. And then for each value, we dynamically choose the best value for x2. So first, we look at red. So x1 is red. What's the best value for x2 in this case? It would be blue. So we cross out this row. We say, if x1 is blue, then x2 is going to be red, because that gives us the biggest. And then, just like before, now for any value of x1, the value of x2 is already set. It's fixed. It's decided. And so that means that we can drop this variable out of the graph, because we've already internally optimized into this function what its value would be. And so this gives us, again, a new table where we have x1. We have the values it can take on, red and blue. And then we have the weights associated with that, which is now 7 and 3. So in math, what that looks like is where we used to have this binary factor. We've now ripped x2 out of the graph, and we have this new factor, this is a unary factor now, which internally optimizes over x2. It says, give me my x1, give me an x1. And then as soon as you get my x1, I'm going to spin through all my values of x2 and give you the best one that would, the best match for it. So what this would look like in pictorially, I guess, is every time you remove a factor, you take all the factors that touch it and you rope them all together and you merge them and into one big factor. And then internally what that factor is doing is it's optimizing over whatever variable you just removed. So for example, if we have, for example, we have this kind of coloring problem. Let's say we want x1 to be red and x4 to be red. What's the best value of x3 that we could give? So over here, we say x1 is red, x3 is red. That gives us a value of 4. And then 3 to 4, red, red, gives us a value of 1. So we have a 1 in here. The other value that x3 could take on would be blue. So now we go from red to blue, which gives us a value of 1, and then blue to red, which gives us a weight of 2. And so we multiply those together, we 1 times 2, which is 2. And then internally, what this factor is going to do is it's going to maximize over those and choose the value for the deleted variable that maximizes, that internally optimizes it for this local problem, which in this case is red. So just another example, if we did red-blue, so x1 is red, x4 is blue. There's 2 options for x3. First, it would be red. So if we go from red to red, that's 4. And then from red to blue is 2. So we go 4 times 2 here. And then the next thing would be if x3 is blue. So we go from red to blue, which is 1. And then blue to blue, which is 1. And that's 1 times 1. And then we would say, oh, well, in this case, the best value of x3 would be red. So it's kind of like internally optimizing. In general, what this looks like is you rip the node out of the graph, you take all the factors that used to touch it, and you tie them all together into one big factor. And again, that's kind of the mathematical notation. There's another way of interpreting this that might be helpful to some people. Basically, it's like I pick my value, and then I'm going to look at all the variables in its Markov blanket, and I'm going to repeatedly condition on every assignment that blanket can take on. And then for each of those conditionings, what's the best value of my selected variable? That's kind of what's going on behind the scenes. Yeah.
Wait, if ripping out random variables and constructing new factors leads to like faster execution times, why don't we just rip out all of the variables except for one, and then it becomes a unary factor and a unary random variable?
Yeah. So the question was, if it's faster to rip out variables, why don't we just do it for the whole graph? And we totally will. Yeah, you'll see. It's in a couple slides. That's the algorithm. So like we have this strategy for ripping out variables, and then the next step is to use it to solve the CSP, which is what we're about to do. Yeah. OK, so there's this question, which I think is cool. So if we have some kind of a star-shaped graph, so if we have a setup, let's say we have a setup like this, which a bunch of factors going into our hub. And we have this variable, we'll call it S. Do we want to run elimination or conditioning on S? I hear some whispers, but yeah?
Conditioning.
Yeah, conditioning. And the reason for that is that if we condition, then all these turn into unary factors. And if we eliminate, then it turns into one giant factor, which is harder to solve. Okay, so like you were saying, this is the algorithm that you get out of it. So basically what you do is you loop through all your variables, and you eliminate them all in turn. And then at the end of the day, you're going to have one variable to rule them all. And that variable will just hold the best answer. Yeah?
To the degree algorithm, can we not run into a case where if we don't have a smart way of choosing which variable we're conditioning on, can we not end up in a case where we have conditioned over this one and that one, it turns out there's no more possibility for
Yeah.
the rest of the graph or whatever?
Yeah, so the question was, wait a second, doesn't ordering still matter? Like, can't we still end up somewhere that's not good? And that's totally true. So towards the end of this lecture is a discussion on exactly that topic. Variable ordering does matter. And it's actually hard. It's an NP-complete problem is to decide the best variable ordering. But so I think I'm going to do one more example I'm going to run elimination on a whole graph, which I think will be helpful. So our graph so we have three variables. We have x, we have y, and we have z. And they're all connected through a single factor. I'm going to write out the whole table for this. So we have x, we have y, and we have z. And let's say they have two values. They could be a or b. So we have a, b. I'm going to run out of space. A, b, b. A, B, A, B, A, A, B, A, B, 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 A, and B, B, B. Is that everything? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay, so hopefully this is readable. And they have weights, right? So we can just arbitrarily say they're 1, 2, 3, 4, 5, 6, 7, 8. Can people make this out? Seems like maybe. So I will go with it. OK, so what do we do? Let's say we want to choose z first. We want to eliminate z. So what we do in elimination is we say for all the variables in z's Markov blanket, we're going to repeatedly condition on the values that they can take on. And then we're going to dynamically choose the value of z that would best match that. So x and y could either be a and a. So this is a. And in this case, the best value of z would be b. Right? So we cross this out. Next, x and y could be a, b, in which case the best value of z is a. So we cross this out. It could be ba, which would be b, or it could be bb. And the best value of z in this case would again be b. So again, like we've seen a couple times before, now for any value of x and y, the value of z is already decided. It's set. It's pre-computed. So we can just drop this variable from our table, which is equivalent to dropping it from our graph. OK, so now we're going to work on y. Again, we do the same thing. We say for each value in y's Markov blanket, which is x, we repeatedly condition on all the possible values it could take on, and then dynamically choose the best value based on that. So if x is a, so now we're comparing. So now we're comparing these two. So if x is a, what's the best value of y? it's b. So we can cross this out. Now, if x is b, what's the best value of y? It's, again, b, so we can cross this out. And now, again, for every value of x, we've decided b, and so we can drop this from the graph. And now what we have is, now we have one variable in our graph with a unary factor. So we have x, and x can be a, or it can be b. And if x is a, then it has a value of 4. And if x is b, then it has a value of 8. And now what we can do is we can just say, OK, we're going to choose x to be 8. And then in kind of implementation, all you would need to do is kind of like look back. You could store some kind of like back pointers or store your old tables, and you can recover your solution from the whole graph from this endpoint. So that is variable elimination. Yeah.
For the second for loop, why do we go in the opposite order from n to 1 instead of 1 to n?
Oh, that's basically, that kind of is a mathematical way of saying what I just said about the back pointers. So it's like now we've gone forward and we've eliminated, and now we can go backward to say, OK, x is b. Now that we've decided x to be b, like we look at our old table and be like, what was the best value of y that gave us that decision? So it's kind of like once you go forward to eliminate, you get your solution, and then you go back and like read off the values as you go. Yeah. OK. So in terms of runtime, basically what you could say is, so for each variable, it's going to have domain to the, so every variable is going to have domain to the arity, the factor touching so the factors touching, like the factor you create from eliminating a variable is going to have this many rows in it. And then there's n variables that you have to eliminate. And with the reason why it's max arity is because if you have, let's say you had some kind of graph that looks like this, this factor would be d squared, the domain squared, and then this factor would be d3. And so like as you're eliminating, going through this graph, like this is just going to dominate d2. So it's as you're going through and eliminating the graph, the arity of the biggest factor you've created is going to bound your performance. And that's where variable ordering gets in. So what is it? Yeah.
So where is +1?
Yeah. So the +1, I'm not actually sure. I thought about it. I looked around and I wasn't able to explain it. So yeah. OK, so but as you're going, order matters because if you looked at this, there's two ways to do it, right? So if you went from the leaves and eliminated each leaf variable first, then all the factors you create would have arity 1. It'd be super easy. But if you eliminated x1 first, then you get this huge giant factor that gives you this big table with arity 6, which would be very slow. So the order really matters. In general, it makes sense to eliminate variables with the fewest neighbors first. It's a pretty sensible heuristic that in practice works well. And we define this term called tree width, which is saying if you had a factor graph and you're going through doing elimination, the maximum arity of a factor that you create along the way using the best ordering is the true width of that graph. So in general, a true width is very, very hard to compute. But for a few cases, you can kind of reason about it. So for example, if you had a chain, let's say we had a chain. And if I was going through eliminating this, the biggest factor I would create is just a unary, just that little guy, right? So true width of 1. If I had a tree, so it's just like our example before. So if you go from the leaves, again, you can create these little factors, these little unary factors. And so you can get away with 1. If you had a cycle, I'll make my cycle a little bigger. But if you had a cycle, the maximum arity is going to be 2. Because even if you kind of work away from the sides, you're eventually going to end up at something that just connects the last things before you delete them. So it's like you have your cycle, and you chew away at both ends, and you're going to end up with something with just those 2 nodes remaining. And then if you had a n by n grid, if you had an n by n grid, so let's say this just goes on, it's the smaller of the 2. And the reason for that is because if you, let's say you go through and you're eliminating these things, something like that, you're going to end up with something, some situation like this. And once you delete this, you're going to get a factor that ropes them all together. Yeah, so that's true width. Super important, hard to compute. Yeah.
You end up with 2 factors before the last 2 nodes in the cycle. So when you have the case of a cycle,
yeah,
and you're going through elimination,
yeah.
you end up
Yeah, you're right. So it's not the first 2. It's not the last 2. It's the first 2. So when you're, let's say this is my cycle, the first factor I create after I delete that is going to be a binary factor. Yeah. So thank you for that. Yeah, so just to summarize, we learned different ways of solving CSPs today. Beam search, which is kind of like a souped-up version of backtracking, which doesn't always give you the answer, but it's faster. Local search, you get entire things, and then you improve them a little bit at a time. Conditioning, break up the graph into smaller pieces that are easier to solve. And then elimination, which is where it's kind of like in conditioning, except instead of choosing one value for all your factors, you kind of like dynamically choose the value based on the Markov blanket. And that's CSPs. So we will see you on Wednesday.